This planet shouldn't exist. Not in this form, not in this perfect chaos of life and rock. Yet here we are. It's a cosmic anomaly that somehow survived everything the universe threw at it. Imagine the odds. Countless planets out there, dead or never formed, and ours stands resilient amidst swirling chaos, climate shifts, and cosmic hazards. So why does this improbable oasis persist? What hidden forces kept it from collapsing into nothing? Stick around, because uncovering the secrets behind Earth's unlikely existence might just change the way you see everything around you, reminding us that sometimes the most extraordinary things are invisible to the naked eye. The cosmic beginning of a peculiar planet. It's enough to make your brain spin. How did a planet so clearly out of sync with the cosmic norm come into existence? Look at the chaotic ballet of stellar nurseries, supernova remnants, and swirling gas clouds, all seemingly choreographed with precision. Yet somehow, this peculiar planet defied expectations. It's almost as if the universe had a mischievous streak, tossing in a spanner that shouldn't have fit, but somehow did. For a planet to exist in such a strange way, its origins must have been extraordinarily tumultuous. Instead of settling into a predictable orbit or composition, it emerged from a fiery, turbulent birth process that involved more than its fair share of cosmic chaos. The story behind this planet's existence begins with its parent star's birth, which itself was anything but ordinary. Instead of forming quietly within a calm nebula, the star's formation was likely punctuated by nearby supernovae, massive explosions that sent shock waves rippling through interstellar space. These shock waves can compress gas clouds, triggering star formation, but they also spawn a distortion of matter that leads to strange gravitational interactions. It's during this tumult that the protoplanetary disk, the cradle of planets, might have been violently disturbed by passing objects or rogue gases. Such disturbances can cause planets to form with unusual compositions, metal-rich, icy, or even with radically tilted axes, making them stand out from the more common planets that tidy up into neat, spherical bodies. Further adding to the puzzle is the planet's anomalous orbit and composition. Instead of forming with a typical mixture of silicate rock and metals, its internal structure might contain unusual elements, vast amounts of exotic ice, or perhaps a core that's unexpectedly dense due to captured cosmic debris. Its orbit could be highly eccentric, a relic of gravitational stealings and close encounters with other rogue celestial bodies in its star system's messy youth. Cases like these aren't just theoretical. Astronomers have observed planets with highly tilted orbits or unusual compositions, often as remnants of violent planetary migrations. This planet's peculiar traits suggest a history rooted in chaos, a remnant of cosmic battles and environmental upheavals that never settled. What's truly mind-bending is that all of this chaos could have been a necessary ingredient for its very existence. If the universe operated like a perfect assembly line, perhaps planets like this wouldn't bother to appear at all. Instead, they are a product of cosmic upheavals that seem counterintuitive but are integral to creating diversity in planetary systems. This peculiar planet, despite its odd origins and apparent randomness, is a testament to the raw, unpredictable power of the universe. It should not exist, and yet, here it is, living proof that chaos can be an artist's brush, painting planetary landscapes no one could have foreseen. Unusual conditions in the early universe. At first glance, the universe's infancy was an astonishing chaos, an unpredictable soup of particles, energy, and fleeting forces colliding in ways that seem almost impossible to reconcile with the universe we observe today. Right after the Big Bang, conditions were radically different from what we experience now. Temperatures soared to trillions of degrees, so intense that atoms couldn't form. Protons and neutrons existed in a state of quark-gluon plasma, shimmering with energy that defies intuitive comprehension. In this early epoch, matter and energy blended seamlessly, and the sheer density of particles was unthinkably high, making the cosmos a roiling, unrecognizable place. What's truly mind-boggling is that such extravagantly unusual conditions didn't last long. Yet they set the stage for everything afterward. The universe expanded rapidly, cooling as it grew, but during its nascent moments, the laws of physics behaved differently. For example, fundamental forces only started differentiating from one another after a fraction of a second, meaning the strong nuclear force, weak force, electromagnetism, and gravity weren't distinct in their current forms. The universe's initial homogeneity was punctuated by tiny quantum fluctuations, imperfections that would eventually give rise to galaxies, stars, and planets. Without these initial weirdnesses, structure might never have formed at all. Delving deeper, some researchers speculate that the early universe might have experienced phase transitions, periods where its physical properties shifted dramatically, similar to water freezing into ice, but on a cosmic scale. These transitions could have produced rare phenomena, like cosmic bubbles or topological defects, which are hypothetical remnants predicted by certain grand unified theories. Such features are not observed directly, but their potential existence speaks to just how unpredictable early conditions were. The universe might have even undergone periods of inflation, exponential expansion, drastically stretching out tiny quantum fluctuations to cosmic proportions, creating the seedbed for all future cosmic structure. Without these bizarre, fleeting states, the universe's extraordinary complexity might never have emerged. The sheer improbability of our planet's existence hinges on these peculiar early conditions. Consider that if the universe hadn't cooled at just the right rate, or if certain phase transitions hadn't occurred, matter, as we know it, might never have coalesced. The initial conditions were so unusual that they seem almost tailor-made, yet they occurred naturally due to quantum mechanics and high-energy physics. It's a stark reminder of how delicate and fleeting such cosmic experiments are. The very fact that stable atoms, complex chemistry, and eventually life could emerge from this primordial chaos makes one wonder what other extraordinary phenomena might have played a role. The universe's early moments are a wild, unpredictable dance that somehow, against all odds, laid the foundation for everything we see today. The rare formation of a habitable zone. It's staggering to consider that planets capable of supporting life are so incredibly rare, especially given the delicate balance necessary for a habitable zone to form. The concept initially sounds straightforward. A star needs to have planets at just the right distance, neither too close nor too far, to sustain liquid water. But the reality is far more complex. Such zones depend on a multitude of variables, from stellar brightness and planetary atmosphere to orbital stability and the planet's composition. The conditions that create this perfect Goldilocks zone happen so infrequently that their existence often feels like a cosmic coincidence. One of the most surprising aspects is how specific the necessary conditions are. For a planet to reside in a habitable zone, it must have just the right amount of stellar radiation to keep water from boiling away or freezing solid. The star size and temperature are paramount. Too hot, and the zone shifts outward, making planets closer and uninhabitable. Too cold, and the zone shrinks inward, leaving planets at safe distances too frigid for life. Earth's position relative to the Sun exemplifies this fine-tuned balance, but such precision is not a given. Many star systems either don't have planets in the right orbit or have planets within hospitable atmospheres that negate potential habitability. Furthermore, the formation of a stable habitable zone requires a perfect confluence of planetary formation processes. A planet must form in the right part of the protoplanetary disk, avoiding excessive asteroid bombardment or volcanic activity that could strip away atmospheres or render a planet dead. Even subtle shifts in planetary orbits over time can move a planet out of the habitable zone entirely. The interplay between planetary mass, atmosphere retention, magnetic fields, and orbital dynamics results in a fragile scenario, one that might be so rare that Earth's abode in the Sun's habitable zone is practically an anomaly when viewed across the universe. It's this fine line, where a planet's climate, atmosphere, and orbital mechanics align perfectly, That underscores just how unique and extraordinary the habitable zone really is. The existence of planets like Earth, orbiting stars with just the right properties, is almost like a cosmic fluke. And yet, despite the odds, this rare combination exists somewhere out there, making the universe a place where life could potentially flourish. The rarity amplifies the awe, an intricate ballet of astrophysics, where countless factors must converge precisely. And when they do, the result is a small oasis in the vast emptiness of space. Unexpected elements in the planet's composition. The idea that this planet could be teeming with elements entirely unanticipated, despite its familiar blueprint, feels almost surreal. We tend to think of planets as colossal spheres composed mainly of elements like iron, oxygen, silicon, and magnesium, elements that we've identified through centuries of scientific probing. But when analyzing Earth's crust or core, researchers bump into surprises that challenge our traditional understanding of planetary formation. For instance, the discovery of unusual mineral deposits and isotopic anomalies points toward influence from processes or materials outside the standard model. Sometimes, rare elements appear in quantities that defy expectations, hinting at complex histories that include asteroid impacts, volcanic activity, or even unknown forms of geological recycling. One particularly shocking example is the presence of elements like osmium and iridium at global scales, elements typically associated with extraterrestrial material or deep Earth processes. These elements are rare on Earth's surface, but appear in significant quantities in certain sediment layers, especially at the boundary between the Cretaceous and Paleogene periods. Their abundance has often been linked to asteroid impacts. Yet their uneven distribution raises questions about how such materials were incorporated into Earth's crust in the first place. This not only hints at a complex history involving cosmic influences, but also suggests that Earth composition isn't solely a product of internal planetary processes, but also the result of external, unexpected contributions. Even more startling are the discoveries of elements that aren't prominent in our planetary models, like xenon isotopes. Certain heavy isotopes, which are usually considered byproducts of radioactive decay, appear in ratios that don't match standard decay chains. This hints at the possibility that some of these elements could have originated from more exotic or unknown sources, perhaps remnants of primordial cosmic events. They're woven into Earth's very fabric in ways that science still struggles to explain fully. Such anomalies serve as a reminder that even our most well-studied planet harbors secrets, elements scattered throughout its crust and mantle that defy straightforward explanation and force scientists to reconsider assumptions about planetary genesis. In essence, the planet's composition offers an ongoing puzzle, an intricate mosaic woven not solely from predictable minerals and common elements, but from unexpected, sometimes bizarre contributions. These surprises keep the scientific community alert, sparking debates over the true origins of Earth's material makeup. Each anomaly adds a layer of complexity that continuously reshapes our understanding of planetary formation and evolution. It's a testament to how much remains hidden beneath the surface, lurking in the depths of Earth's unseen layers, waiting to rewrite what we think we know about the very foundation of our world. Mysterious climate and environmental anomalies. Every so often, the planet throws a curveball, climatological quirks and environmental oddities that defy logical explanation, leaving scientists scratching their heads. Take, for instance, the sudden and localized spikes in temperature that appear in areas otherwise known for their cold climates, like certain regions of the Arctic spawning unseasonal warmth. These anomalies aren't just minor fluctuations. They can disrupt entire ecosystems, melt ice sheets unexpectedly, and throw off climate models that are supposed to predict future conditions. Such phenomena challenge our understanding of atmospheric and oceanic interactions, raising questions about what unseen forces or unknown variables might be influencing these irregularities. Then there's the bizarre case of atmospheric rivers. Massive columns of vapor transporting moisture across great distances, sometimes depositing torrential rain in places that aren't traditionally prone to such weather. The scale and frequency of these events seem to be intensifying in ways that science can't yet fully explain. When a single atmospheric river dumps enough water to fill hundreds of thousands of Olympic-sized swimming pools onto a single city in a matter of hours, it fuels flooding and infrastructure damage. Yet the mechanisms behind their increased activity remain partly shrouded in mystery. Some suggest climate change may be amplifying their intensity, but pinpointing precise causes proves elusive, especially when these events seem to arise suddenly or in places where they've historically been rare. Environmental anomalies aren't limited to the atmosphere. Ocean currents, which are vital for regulating global climate, have started behaving unpredictably. The Gulf Stream, a key conveyor belt of warm water, has shown signs of slowing down and shifting positions, an unsettling development that could lead to drastic changes in weather patterns across Europe and North America. These shifts could be linked to melting ice caps, which introduce fresh water into saline ocean systems, disrupting the density-driven movement of currents. However, the rapidity of these changes, coupled with the unpredictability, suggests that just understanding the basic physics isn't enough. We're witnessing a complex, interconnected puzzle that seems to keep changing right before our eyes. Adding to the enigma are mysterious environmental phenomena that don't fit existing scientific frameworks. For example, sudden dead zones, areas in oceans where oxygen levels plummet and marine life perishes, are expanding and occurring in places previously considered stable. Some researchers suspect that unknown chemical pollutants, perhaps from emerging contaminants or even natural sources we haven't yet identified, could be contributing. Meanwhile, unexplained increases in atmospheric aerosols and particulate matter in remote regions have been linked to silent, large-scale volcanic or geological activity, but definitive connections are hard to establish. It's as if the planet is constantly whispering secrets through these anomalies, yet only fragments of the story emerge, leaving us both in awe and alarmed at how little we truly understand about the delicate balance of Earth's climate and environment. The enigma of stable oceans and atmosphere. The idea that oceans and atmospheres can maintain such a delicate balance over vast expanses of time feels almost like a cosmic trick. Think about it. Despite countless forces that could easily tip the scales, like violent storms, shifting tectonic plates, or the relentless energy from the sun, Earth's oceans and atmosphere remain in a surprisingly stable state. This stability isn't a given. It's a finely tuned dance of physical, chemical, and biological processes that constantly adjust and counterbalance each other. The fact that the oceans don't just evaporate into space or freeze solid is astonishing, considering the raw energy constantly bombarding our planet and the chaotic nature of planetary systems. The atmosphere's ability to retain just enough greenhouse gases, like carbon dioxide and methane, to keep surface temperatures within a life-friendly range is another baffling aspect. Levels of these gases fluctuate, yet overall, they stay within bounds that prevent runaway ice ages or unbearable heat. This balance involves complex feedback mechanisms, like the carbon cycle, where oceans act as massive carbon sinks, absorbing excess CO2 and releasing it during periods of imbalance. Phytoplankton photosynthesis, for example, captures carbon from the atmosphere, helping regulate its composition. This process alone highlights an incredible ecosystem service that keeps our planet habitable despite the chaos of outside forces. Not only are chemical processes at play, but physical phenomena contribute to this stability too. Ocean currents, driven by temperature and salinity gradients, distribute heat across the globe in ways that temper extreme temperatures and maintain climate zones. The Gulf Stream, for instance, transports warm water from the tropics to the North Atlantic, preventing Europe from freezing over and showing how interconnected and resilient these systems are. Meanwhile, atmospheric circulation patterns like the jet stream guide weather systems, dispersing energy and moisture. These large-scale patterns are resilient, often restoring equilibrium after disturbances, which seems miraculous given the turbulent energy involved. What's most startling is how these systems overlap and reinforce each other in a kind of cosmic cooperation. The stability of Earth's environment depends on a web of processes, biological, chemical, physical, that have evolved to sustain conditions vital for life. Everything from volcanic activity releasing gases, to oceanic absorption and release cycles, to solar radiation and planetary rotation, all interact in ways that ensure Earth remains a haven rather than spiraling into chaos. It defies simple explanation, almost like complex machinery configured with an intelligence beyond what we typically recognize, making this planet's habitability a wonder that edges on the miraculous. Surprising biological evidence. The resilience of life on this planet often defies what we might logically expect given the extreme conditions some species endure. Take the tardigrades, commonly called water bears, tiny creatures barely visible to the naked eye, that have survived in the vacuum of outer space, endured radiation levels lethal to most life forms, and thrive through boiling heat and freezing cold. Such biological feats seem almost supernatural, but they highlight the incredible adaptability encoded into the DNA of certain organisms. Their unique proteins and cellular structures provide superlative protection, turning what seems impossible into irrefutable evidence that life can persist far beyond what natural logic suggests. Another startling example lies in extremophiles, microorganisms that thrive in environments previously thought uninhabitable. Deep-sea hydrothermal vent bacteria, for instance, live in waters hotter than boiling, under immense pressure, and in complete darkness. Their metabolic pathways are remarkably different from those of most life forms. They often rely on chemosynthesis, converting inorganic molecules like hydrogen sulfide into energy, bypassing the need for sunlight. This metabolic versatility illustrates how life can adapt to seemingly hostile conditions, challenging our assumptions about what environments are truly unlivable and expanding our view of how life might exist elsewhere in the universe. The existence of such biological marvels also raises profound questions about the origins and persistence of life on Earth. Evidence from isotopic anomalies and microbial fossils suggests that some microorganisms have been around for billions of years, surviving mass extinctions and planetary upheavals. Intriguingly, they contain specific enzymes capable of repairing DNA even after intense damage, which might explain their longevity and survival potential. This hints at an evolutionary advantage, an innate resilience, embedded deep within their genetic code that enables them to relentlessly adapt and endure. It boggles the mind to think that complex, thriving ecosystems could originate in such extreme niches, making the overall rarity and delicacy of Earth's hospitable environment all the more astonishing. What truly shocks is how these biological clues hint at the possibility that life's existence isn't just a chance anomaly, but perhaps a natural inevitability, an adaptation potential woven into the fabric of matter itself. From the persistence of ancient microbes underground to extremophiles in toxic environments, these organisms serve as potent evidence that life finds a way, often in places and ways we least expect. It is as though the planet itself whispers a secret, that life's ability to endure, mutate, and evolve is not just a fortunate accident, but a fundamental characteristic of the universe, making this seemingly fragile planet a sanctuary of improbable resilience. The puzzle of long-term climate stability. It's astonishing to realize that Earth has maintained a relatively stable climate for billions of years, despite the chaos of natural forces constantly conspiring to tip the scales. How does a planet, orbiting a star known for its fiery temperament, manage to sustain temperatures that support liquid water and diverse ecosystems over geological timescales? The sheer coincidence of this stability feels almost miraculous, given the constant fluctuations arising from volcanic activity, asteroid impacts, and variations in solar radiation. Yet, somehow, Earth's climate has remained within bounds that allow life to flourish, not just briefly, but for billions of years. This stability hinges on a finely tuned balance of feedback mechanisms. The carbon cycle, for instance, plays a pivotal role. When volcanic activity releases CO2 into the atmosphere, weathering processes on continents and oceans work to draw down that carbon, eventually depositing it as carbonate minerals. This acts as a natural thermostat, preventing runaway warming. Conversely, during colder periods, the reduction in weathering allows CO2 to accumulate, gradually warming the planet once again. This tight regulation isn't perfect, but its overall effect has maintained the planet in a relatively habitable state for eons. It's like a slow, deliberate conversation between Earth's interior and surface conditions that silently regulates climate. The ocean and ice sheets are also crucial agents in this long-term stability. The ocean acts as a vast heat reservoir, distributing solar energy across the globe and buffering temperature extremes. Meanwhile, ice sheets have a reflective property that helps prevent runaway warming by bouncing sunlight back into space. During ice ages, these mechanisms work strongly to plunge Earth into colder conditions, and during interglacials, the ice melts and the climate stabilizes again. The existence of these large, dynamic systems operating in tandem suggests that a delicate equilibrium exists, essentially balancing the planetary climate for millions of years without tipping into chaos. Yet, the challenge today is that this fragile system is under threat. Human activities, especially the rapid release of greenhouse gases, threaten to disrupt these ancient, evolved feedbacks that have kept Earth in balance for so long. The shock isn't just that climate could shift. It's that the universe has granted Earth this remarkable stability, a gift that's almost too good to be true when considering the relentless natural forces at play. We've only recently begun to understand how fragile this balance truly is, which makes the question of why Earth should be this stable, rather than a volatile, inhospitable world, a mystery with profound implications. Unexplained geological features. It feels almost surreal to consider that our planet, so meticulously mapped and studied, harbors features that defy everything scientists believe about Earth's geological processes. Take the Giant's Causeway in Northern Ireland. Thousands of interlocking basalt columns forming a seemingly perfect tessellation. Most explanations point to ancient volcanic activity, yet the precise mechanics and timing remain debated. The column's columnar jointing appears almost engineered, yet nature's randomness molds them. Such formations challenge conventional understanding of volcanic cooling and contraction, hinting at anomalies that scientific models struggle to fully explain. Then there is the Darvesa crater in Turkmenistan, where a massive natural gas blowout in the 1970s led to a fiery crater that continues to burn relentlessly. The locale defies expectations. No impact crater, no volcanic activity. Yet this sprawling, self-sustaining flame persists without clear origin. Its depth and concealed complexity suggest deep methane deposits or other geological phenomena that don't fit typical models. Observing the site feels almost like witnessing a geological enigma frozen in time, one that hints at undiscovered or misunderstood processes beneath Earth's crust. Another astonishing example is the Pingualut crater in Quebec, a perfectly circular, glassy lake nestled within a seemingly pristine crater. While its shape resembles impact sites, no confirmed meteorite has ever been found, nor do impactor traces exist. Instead, some scientists propose it's a collapsed dome or a volcanic maar, but the symmetry and pristine condition of the crater complicate these theories. Its existence raises questions about ancient geological activity that might have been erased or entirely different from current models. These anomalies aren't just oddities. They challenge scientists to rethink the fundamental mechanisms shaping our planet. The sheer variety and mystique of these geological features provoke a profound curiosity. They serve as reminders that Earth's surface still guards secrets that don't align neatly with established theories. Each unexplained formation beckons further investigation, hinting at deeper layers of geological history. While science continually advances, some features stand as silent witnesses to processes that may have played out in ways we've yet to fully fathom. It's almost as if Earth's own architectural blueprint contains unanticipated signals, echoes of a planet still revealing itself slowly, if at all, perplexing orbital mechanics and positioning. It's staggering to think about how Earth maintains its delicate balance in a seemingly chaotic cosmic dance. The planet's orbit isn't just a simple circle circling the sun. It's an intricate waltz governed by gravity, momentum, and countless tiny influences that can shift its path over millennia. If you peer into the mechanics, you'll find that Earth's orbit is slightly elliptical, not quite a perfect circle, which means the distance from the sun varies throughout the year. Those variations, though often imperceptible to us, are essential for climate patterns, seasonal shifts, and even the stability of life itself. Yet, internal and external gravitational forces constantly threaten to disrupt this balance, from the tug of planetary neighbors to the subtle influences of passing celestial objects. The positioning of Earth isn't only about the sun. It involves an elaborate interplay with other bodies in the solar system. The gravitational pull from Jupiter, because of its massive size, can cause tiny but significant fluctuations in Earth's orbit over long timescales. This phenomenon, known as orbital perturbation, can slowly shift Earth's elliptical path, affecting climate cycles known as Milankovitch cycles. These subtle shifts can change the severity and duration of ice ages and interglacial periods, illustrating how fragile our planet's orbital stability truly is. It's almost miraculous that, despite these vast, ongoing influences, Earth's orbit has remained relatively stable, allowing complex life to flourish. Orbital resonance also plays a surprising role in our planet's positioning. Earth's orbit interacts with other planetary orbits in a way that prevents catastrophic overlaps or collisions, a cosmic choreography that's both precise and astonishing. For example, the gravitational relationship between Earth and Venus prevents close encounters over millions of years, thanks to their orbital resonances. These complex gravitational relationships are not static but evolve with time, requiring continuous adjustments in our understanding of celestial mechanics. This intricate web of interplanetary influences illustrates just how finely tuned our planet's position is in the grand scheme of the solar system. What's truly mind-boggling is that these processes are ongoing and dynamic. Small variations, if amplified, could lead to drastic changes in Earth's climate or even its orbital stability. Yet, everything seems to align just perfectly, at least for now. The delicate balance of gravitational forces, orbital eccentricities, and resonances forms a cosmic stability that, if it were slightly altered, might make this planet unrecognizable or even uninhabitable. It's almost humorous that such complex, interconnected systems keep Earth ticking, like a cosmic clockwork that doesn't quite fit our intuition, yet somehow manages to work flawlessly for billions of years. The astonishing resilience to catastrophe. It seems almost impossible that Earth, battered by relentless asteroid impacts, volcanic eruptions, and extreme climatic shifts, has persisted through billions of years of chaos. One moment, the planet faces a catastrophic event that could wipe out entire ecosystems, and yet somehow it always finds a way to bounce back. The fact that life, diverse, complex, and resilient, continues to thrive is nothing short of astonishing. For example, after the Permian-Triassic extinction, which wiped out an estimated 90% of marine species, life rebounded in remarkably rapid ways, giving rise to entirely new groups of organisms. This pattern of devastation, followed by recovery, highlights a resilience that defies natural expectations for such chaos. On a planetary scale, Earth's resilience is driven by an intricate web of feedback mechanisms. The carbon cycle, for instance, plays a crucial role in regulating climate and atmospheric conditions. When volcanic eruptions pump vast amounts of greenhouse gases into the atmosphere, life and the planet's geochemical systems work tirelessly to restore balance. Oceans absorb excess carbon, forests, and even underground reservoirs sequester carbon dioxide, mitigating catastrophic runaway warming. This capacity to self-regulate, despite massive disruptions, is astonishing. It's as if Earth possesses an innate capacity to adapt and recover from almost anything thrown at it, often over timescales that stretch human comprehension. Natural resilience is not just about chemical cycles. Ecosystems themselves adapt with an almost stubborn refusal to give up. Take the example of the microbial communities deep within the Earth's crust. They survive temperatures that would obliterate most forms of life, thriving in conditions that are essentially the planet's underground resilience hubs. When surface ecosystems are obliterated by disaster, such microbes can serve as a seed bank, enabling life to recolonize and rebuild from below. These hardy communities underscore the extraordinary capacity of life to endure, persist, and recover even in the face of overwhelming adversity. The resilience of Earth also relies on the gradual geological processes that shape its surface. Plate tectonics, despite triggering earthquakes and volcanic activity, continually rebuild the planet's landmass and generate new habitats. This slow but relentless process creates a perpetual cycle of destruction and renewal. Mountains erode, sediments are recycled, continents drift apart and collide, each cycle fostering opportunities for new life to evolve. It's almost as if the planet is wired with an evolutionary instinct to persist, no matter the trauma. The resilience to catastrophe isn't just a feature of individual species or ecosystems. It's embedded into the very fabric of Earth itself, making its continued existence all the more extraordinary amid a universe rife with destructive forces. Unraveling the fine-tuned balance of life. It's startling to realize that our planet exists within such a narrow window of conditions that support complex life. The Earth's distance from the Sun, roughly 93 million miles, places it precisely where temperatures stay within a range that keeps water in a liquid state, a fundamental ingredient for life as we know it. Slight deviations in orbit or solar radiation could render the planet either a frozen wasteland or a bubbling, uninhabitable inferno. The atmosphere's composition, about 78% nitrogen and 21% oxygen, has persisted long enough to sustain countless species, yet any significant imbalance could lead to suffocation hazards or runaway greenhouse effects. The fine-tuning involved here feels almost miraculous, especially considering how volatile planetary systems can be. Further complexities emerge when you consider Earth's magnetic field. Generated by the swirling motions of molten iron in the planet's core, this magnetic shield deflects solar wind and cosmic radiation that would otherwise strip away the atmosphere or bombard life with harmful particles. Without this protection, Earth's atmosphere could have eroded rapidly, exposing the surface to deadly radiation levels. The existence of such a robust magnetic field isn't guaranteed. It hinges on specific conditions deep within the Earth's interior, which seem to be a rare happenstance in planetary formation. This subtle layer of protection plays a pivotal role in making Earth's surface hospitable, yet it exists only because a series of improbable conditions align. The delicate balance extends to Earth's biosphere as well. The presence of liquid water, the availability of essential elements like carbon, nitrogen, and phosphorus, and a stable climate all intertwine to form an environment where life can flourish. Photosynthesis, the foundation for most food chains, requires specific atmospheric gases and sunlight that aren't overly intense, preventing the surface from becoming scorching or sterilized. Marine ecosystems, terrestrial plant life, and the entire web of biodiversity depend on these intertwined factors remaining within narrow limits. Any slight shift, be it from volcanic activity, asteroid impacts, or changes in solar output, could tip this balance and disrupt the entire structure. It's almost unfathomable how these factors converge simultaneously to create a planet capable of supporting complex, diverse life. Many planetary systems lack the right combination of orbital stability, atmospheric composition, or magnetic protection. The fact that Earth is a rare gem in a universe filled with potentially hostile environments hints at an underlying cosmic randomness or possibly some grand guiding principle. Yet, amidst this vast, seemingly chaotic universe, our tiny blue planet stands as a testament to this unique, precarious balance, an extraordinary confluence of circumstances that make life not just possible, but sustained over billions of years. The paradox of existence despite odds. The sheer improbability of a planet like Earth existing boggles the mind when you consider the vastness of space and the chaos of cosmic events. It's startling to think that amidst billions of stars, countless planets, and an almost endless universe, this tiny sphere became the cradle of life. Every element that makes Earth habitable, its perfect distance from the sun, a protective magnetic field, a stable atmosphere, seems like a bizarre stroke of luck considering the chaos in the cosmos. Supernovae, asteroid impacts, gamma-ray bursts, all lethal events racing through space, should have wiped out life or prevented it from ever taking hold here. Yet, somehow, everything aligned just right for life to emerge and flourish. This paradox is amplified when factoring in the fragile balance required for complex organisms to thrive. Earth's position in the so-called Goldilocks zone makes it uniquely suited for liquid water, a fundamental ingredient for life. But it's not just location. The planet's composition, geological activity, and even the presence of a large moon contribute to a stability conducive to life's development. These factors are interconnected in ways that seem almost too coincidental. For example, the moon's gravitational pull stabilizes Earth's axial tilt, reducing extreme climatic shifts. Such an intricate dance of cosmic coincidences makes our very existence feel like a miracle, an improbable confluence of conditions that ought to be astronomically unlikely. And what about the sheer number of variables that had to go right for life to even begin, let alone evolve into everything we see now? The formation of organic molecules in primordial oceans, the rise of simple life forms, the evolution of multicellularity, all these steps required precisely the right chemical conditions and environmental pressures. Despite the chaos and violence of the universe, something about Earth's early environment created the perfect cocoon for life to start. It's as if the universe, in some strange way, was nudging toward the emergence of life, or at least the kind of planetary conditions that can nurture it, against all odds. This realization invites a mixture of curiosity and awe about the universe's hidden biases and patterns. Why did conditions conducive to life emerge on just one planet among billions? Was it pure chance? Or is there an underlying principle that favors planets like ours? Some scientists speculate that the universe's physical laws tend to produce habitable worlds given enough time and diversity of environments. Others suggest that our existence could be a fluke, a rare event in a universe brimming with inhospitable worlds. Either way, the fact remains, life, and Earth itself, stand as a testament to the universe's uncanny ability to produce something that seems almost impossible. The paradox of our existence continues to challenge our understanding and fuels a relentless curiosity about whether we are truly unique or just a fortunate anomaly in an endless cosmic expanse. Implications of a planet that shouldn't exist. It's startling to think that a planet could exist against the odds, defying what current astrophysical models predict should be the case. When astronomers find a planet orbiting its star in a way that crunches the numbers and contradicts our understanding of planetary formation, it leaves everyone reeling. These planets might orbit too close or too far from their stars, possess unexpected chemical compositions, or have strangely tilted axes. Yet, somehow, they're still out there, thriving in environments that seem improbable or impossible. This raises profound questions about the very mechanisms we believe govern the universe. The implications ripple through our understanding of cosmic laws. If planets form under specific conditions, and those conditions aren't as universal as we thought, then our models need significant revision. It's like discovering a new piece of a puzzle that doesn't fit, forcing scientists to revisit theories of accretion, gravitational collapse, or even the influence of nearby stars. For example, a planet with a highly eccentric orbit that should have long since spiraled into its star would challenge the stability assumptions we hold. Yet it persists. Such anomalies suggest there might be unknown factors at play, perhaps unconventional forms of planetary building blocks or novel gravitational interactions. There's also a broader curiosity about whether these impossible planets influence their local environments in unexpected ways. Could they harbor conditions ripe for life despite supposedly being in inhospitable zones? Their very existence hints that our previous criteria for habitable zones, based on temperature and radiation levels, might be incomplete. If planets that should be inhospitable are stable and possibly even teeming with life, it forces us to reconsider where life could exist. The universe might be more resilient and adaptable than our current models suggest, expanding the potential for finding life in unexpected places once deemed impossible. Finally, the existence of such planets could have ramifications for future space exploration and even asteroid or planet colonization efforts. If planets thought to be inhospitable are actually stable and capable of supporting life or human activity, it's a game changer. It might mean that our criteria for what makes a planet worth exploring need an overhaul. Perhaps what we dismiss now as unlikely or impossible will become the most intriguing targets in the hunt for extraterrestrial life. It's almost poetic, planetary boundaries shattered, expanding the horizon of what's achievable and what we should dare to explore. It's shocking to think about how precisely our planet's conditions align to support life, especially considering the absurdly improbable chain of events that made Earth habitable. The idea that such a planet should even exist in the vast, cold expanse of space seems almost narcissistic, like stumbling upon a perfectly tuned greenhouse floating aimlessly in the universe. The delicate balance of Earth's atmosphere, the presence of liquid water, the tilt of the axis, and even the existence of a protective magnetic field. All these factors seem like cosmic coincidences that shouldn't have happened simultaneously. Yet, here we are, standing on a planet that defies all odds. Underlying this apparent improbability is a series of interconnected cosmic mechanics that defy naive expectations. Our solar system, for example, wasn't always destined to give birth to a planet capable of supporting complex life. Jupiter's massive gravity played a role in shielding Earth from constant asteroid impacts, but even forming a stable orbit was a matter of luck. The right concentration of elements such as carbon, oxygen, and nitrogen needed to create a biological inventory wasn't guaranteed. These elements had to be sprinkled throughout the nebula from which the solar system coalesced. Without this precise distribution, Earth might have been just another barren rock, utterly inhospitable. What makes this even more perplexing is how Earth's particular history diverged from countless other planetary candidates. Many planets in our galaxy are tidally locked or have extreme atmospheric conditions that render them uninhabitable. Yet, Earth's tilt and the presence of a relatively stable climate have allowed for stable ecosystems to develop. The emergence of life itself, from simple microbes to complex organisms, hinges on this delicate interplay. It's as if the universe, in some unfathomable way, tried repeatedly to produce a planet capable of supporting intelligent life, with countless iterations ending in failure. Yet somehow, Earth came through as a triumphant exception. Thinking about these layers of improbability stirs a mixture of awe and curiosity. How many other planets might be hiding in the galaxy with similar or even better conditions? Could a planet like ours be a rare jewel in the universe's vast wasteland? Or is Earth merely one of countless similar spheres that we haven't yet detected? The odds seem stacked against such a perfect alignment of factors, and yet it exists. That paradox invites further questions about the nature of cosmic happenstance, about whether our existence is a fortunate byproduct of random chance or a sign of something deeper, perhaps purposeful, lurking somewhere beyond our understanding. It's almost impossible to believe that a planet like this could exist, so seemingly random, yet perfectly balanced in ways we're only beginning to understand. From the chaos of cosmic forces that shaped it to the delicate conditions that sustain life, this planet defies expectations at every turn. How'd it all come together? And what does that say about the universe's grand design, or lack thereof? It's a puzzle that leaves us both amazed and curious, making you wonder if this isn't just some extraordinary fluke or something more significant. If you're as captivated as first and by the mysteries of our universe, stick around. Future videos will delve even deeper into these cosmic questions, uncovering secrets that might someday change how we see everything. So, don't forget to like, subscribe, and join the journey, because what we discover next could be even more mind-blowing. Thanks for watching, and see you in the next adventure into the unknown.